So yeah, today my name is Elena Nieddu. I am a PhD student at Roma 3, which is the third university of Rome. And I will be giving a talk about a research project that is going on at our university. It is an interdisciplinary research project because it both involves us, the data scientists, and, ooh, okay, maybe I have to talk like, okay, softer. And as well as paleographers and archivists, and we're focusing on the world's largest collection of historical documents, that is the Vatican Secret Archive. So, a few things about me. That's something I already told you. My main research interests are in knowledge extraction and machine learning. I have been using Python as my main programming language since 2014, and I have done the project since 2017. The project has been active since 2016, so since almost the very beginning. And I am here, even though this will be a very, not very technical topic, very technical talk, because most of our project code is in Python, and Python enabled us in all of the steps of our pipeline. And oh, I forgot to leave that in Italian. Yeah, most of the code is also my fault. That means that is my fault, it's colpa mia. And so this is why I'm here to give this talk. So a brief overview of what we will be going through. We will talk about some concept about knowledge extraction, what does it mean, and especially what it enables us to do. And the Vatican Secret Archive, what it is really, why it's not really secret, and what we're doing in there, and why we need machine transcription. And the challenges we have faced and we are facing, and how we are currently solving our problem. And then a few, I guess I will be taking 10 minutes or so for the questions. Okay, so first, knowledge extraction. You will, maybe you have noticed that right now you can ask natural language queries to Google. You do not search for keywords anymore, or, well, you can do that, but you can also perform search in natural language. So you can ask questions. You can say, who is the director of Apocalypse Now? And you do not get only a list of pages containing the words, who is the director of Apocalypse Now? But you get a full, detailed answer. Like you get the name, Francis Ford Coppola, and you get Apocalypse Now director. And you can solve more steps than one, because you can ask more articulate questions. For example, you can ask, who is the wife of the director of Apocalypse Now? Which means first you have to solve who is the director of Apocalypse Now, and then you have to solve who is his wife. And then again, you can ask that, and you will get a singular answer. One answer, that is Eleanor Coppola, and you will have there Francis Ford Coppola, which is the solution to the first question, and then spouse, Eleanor Coppola. And you can have third-degree questions, so that they require to solve. We're going incrementally harder questions. So, what is the birthplace of the daughter of the director of Apocalypse Now? So, Francis Ford Coppola, his daughter, and where she's born. And that's New York City, Sofia Coppola. Well, how does Google do that? Because that's not about search, just keyword search anymore. The answer is that by indexing the whole web, they also have access to X-text content. And by analyzing this text content, you can extract entities and relationships and create a knowledge graph. So a knowledge graph is a structured organization of entities and relationships. Okay, maybe I can switch to full screen. Okay, very well. And they are related, and you can search through these links and make even always more and more articulate questions. So at our university, there is another project that is called Lector that does precisely that on web pages, specifically coming from Wikipedia. And Lector was able to extract 3 million new relationships from Wikipedia. But when I say new relationships, I mean that they are not in a commonly known, freely available knowledge base, such as if you're familiar with other knowledge graphs, such as Freebase or some of the Google available data, and so on. So these are new, something that's not yet in any known knowledge graph. And we're used to think of big data and knowledge as something that comes from, and knowledge extraction as something that is performed on web content. But really, there is lots of content that is not on the web and is of unprecedented historical and cultural value. And in Rome, there is well, not quite in Rome, because it's in the Vatican, but we have the largest historical archive, that is the Vatican Secret Archive. And let's talk how big this data is. You might say, well, it will never be as big as the web. And that's true, but it's still quite large. So this is Mount Everest for scale, for reference, and it's 8.8 kilometers. And if you were to take every shelving of the Vatican Secret Archive and stack it on top of the other, you would get a mountain that is approximately 85 kilometers tall. That is almost 10 times Mount Everest. That's how big this historical data is. And also, it's not just big, it's important. So here you can see 4 different documents, and they come from 4 different continents. This one's from Europe, Asia, America, and Africa. And they're all documents that are, for example, this is the letter that was signed by bishops to allow Henry V to divorce, for example. This is a letter from the last Empress of China. This is a letter coming from, I believe, Morocco, and it's a testimony of interreligious relationships. So this letter basically says that how do you say, like the local imam, I think, was in very good relationship with the local bishop. And this is the only testimonials we have of a Native American language that has been transliterated into Latin characters and written on wood. This is a wood tablet. So very, very unique and different type of documents. So what is our goal? Our goal is to perform knowledge extraction from historical documents and building an historical knowledge graph, so that we can search this kind of data faster, better, and in a way that has never, and on a scale that has never been done before. That is, of course, very ambitious, but we have to start from somewhere. And in particular, we are starting from a collection that is called the Vatican Registers. And they are pretty interesting from the historical point of view because they are the copy of the official correspondence of the Pope, which means that every time the Pope was sending a letter, this letter, before being sent, was copied by some specialized people, so that they had a proof that that letter was written, and so that people that, for example, were interested in knowing the Pope's, like what the Pope was saying about some kind of law, before there was canon law, these kind of letters were actually the law, because what the Pope says in an official letter was as good as law. And so, and they span quite a large time frame, starting from the 11th century to the 16th, 17th century. We're focusing on the 20th century, 13th century letters. And this is an actual sample of the text we're working with. And as you may have noticed, it's not really text, it's images. And that's quite the problem for if you want to perform knowledge extraction, because when you have web content, you already have the text. When you have images, then that's pretty different. You need the transcription first. And that is a particular problem of our collection, but it's a pretty general problem, because when you hear that historical archives are digitizing their content, what they do mostly is they're taking pictures, which means that we still need a human to read them. And you might tell me, well, OCR is mature enough. Yes, OCR is mature enough on printed text, but try to and get an OCR system working with that. Good luck. And so this was the first step that we are engaging with. On top of that, you have to understand this is very hard to read, not just because it's in Latin, which is a language nobody speaks anymore, but for the way it's written in. For example, every dash you see here, and these kind of symbols and curls and so on, they are all abbreviations, which is why you can't just ask a person to read that. You need an expert that is a paleographer who is specialized in reading this kind of ancient text. So you might say, well, machine learning has done wonders for us. Let's train a model. And the usual way you go with this is you train at word level. So you train a classificator to recognize, for example, words that are of interest. But we have a problem with this approach, and that is the scalability problem. This is a log-log scale graph, which means actually this relationship is an exponential one. And we're plotting how many words occur how many times. And as you can see, one word has 10,000 occurrences. Only 5 words have 100 occurrences. And there is a very long tail of words that occur less than 5 times. This is on 100 pages, I believe. And so this is how hard it is to collect enough samples for each word. And that does not scale because you need thousands of images. And this kind of images, it's not something you can just put on a crowdsourcing platform and get done. Because, for example, when you're asked to solve civic numbers or a picture containing, for example, stop signs, that's easy. Everyone knows what a stop sign is. But it's not as easy to tell what this word is. Like, what is this? You might say it's 7, no, it's not. And there, so pretty much every word in this line is abbreviated. So it would be very expensive time-wise and, of course, money-wise to get that done. So the picture I'm about to show is how our current pipeline, our transcription pipeline works, and how we're solving the problem right now. Some data is slightly outdated, and I will correct it on the fly. So what is our idea? Our idea is to recognize by character, even if that can be very challenging in some cases. Why recognizing by characters? Well, because that actually enables you to do crowdsourcing. Because what we're doing right now, we have a custom crowdsourcing platform, and which looks kind of like that. We are providing positive examples to the workers, and we're asking them to pattern match them visually. So no actual paleographic knowledge is required. You just have to tell which one of these images kind of look like this one. In theory, you even could use that for writings you can't understand. And then we train a convolutional model that is a classifier. At the first step, we only were recognizing 23 characters that are the characters of the Latin alphabet. But now we have extended the symbol that we are able to recognize to 33. One of these classes is actually a dummy mock class that does not represent one particular character, but rather it represents something that's not a character, a wrong segmentation. Why am I saying a wrong segmentation? Because in traditional OCR, what you would do is you try to isolate each character, then recognize it, and then build a word. That's simply not possible when you're working with cursive script, because there is no clear way to to understand a priori where a character starts and where a character ends. You need more knowledge. For example, you could say that this is a D, but then you could also say this is a D. And in this case, you would be right, but in this other case, you would be wrong, because this is an O, and the link that you see here is just part of this other letter. So you're facing a paradox that is called the Cyrus paradox. That is, you're not able to recognize if you do not segment, and you're not able to segment if you can't recognize. What the way we're trying to solve this is that we over-segment. We do what we call a jigsaw segmentation, because it kind of looks like a jigsaw puzzle. And so we are sure that we have more than we need to compose the characters. And then what we do is we try different combinations, and each of these combinations is classified, and the neural network is able to tell whether it sees a character or it doesn't see a character. If it doesn't see a character, this edge is discarded, like you see here, because they didn't look like any of the characters that the network is able to recognize. Otherwise, if it's a plausible enough characters, the network will classify, will tell you this is a D, this could also be a D, but also this could be an O, depending on which segmentation you will choose. So we're not done yet, right? Because we could have this interpretation saying that this is D-A-I-D or D-A-T-O, which is the correct one, by the way. And so what we do, we need something more than pure visual recognition. We need something that we call experience. And this experience takes the form of a Latin language model, which means that we have computed statistics on substring of a text, of Latin text, of classical Latin text. And so we are able to tell which character sequences are more likely to occur and which ones are not. So we're computing the probability that this is DATO versus the probability that this is DAID, and all of the path you see here. So what we get in the end is not a single transcription, but rather it is a ranking of transcription. And hopefully, if the language model is correct in its prediction, the best one will be the top ones. So both of these corpuses, the image corpus and the word corpus, were collected by us, and I'll go in more detail to how we did it. So first thing first, crowdsourcing. This is an actual screen from the platform. As I was anticipating, we're showing positive examples and negative examples, and we're asking to tick the boxes that kind of look like this, without getting confused with this. And it's a bit like CAPTCHAs, if you have ever solved one. I'm sure you have. For this part, we were able to involve high school students because they were doing the school work experience, and so we involved them on working at the crowdsourcing platform. They also had very small lessons on image processing and machine learning and paleography, of course. And so in this way, we were able to collect over 50,000 annotations over 32 different classes. The other classes inferred for everything that the students didn't mark, actually. And this was a few weeks' work versus months or even years of the same work being performed by experts. And then we realized from their feedback that it could be useful anyways to give them context, and we could get more high-quality annotations by displaying this kind of screen rather than just matching, and this also enabled us to reconstruct the words that we were trying to it enabled us to reconstruct the words that we are asking them to select. Because, of course, they're just being asked to select single pieces inside of this image. But when you get them all, then you can try and reconstruct a transcription, which the former crowdsourcing platform didn't enable us to do. And then this is our model. It's a pretty simple model. And we've been using both TensorFlow and Keras. And there was a bit of back and forth between the two libraries, because sometimes when we started using Keras, it wasn't mature enough, and then we switched back to TensorFlow. And then TensorFlow decided to drop all of the libraries that we were using in the 2.0, which meant we went back to Keras, which now is very nicer and also integrated. And that's very, very useful, because it's also, we get to work with lots of undergraduate and graduate students. And it's nice to have Keras because it enables us to have a common language, so to speak. And the latent corpus I was mentioning, and Scrapy was our best friend in this case, because there is lots of latent, since they have no copyright, there is lots of latent tests available on the web. But usually you don't just get a button that says download the full corpus. So what you do is go through pages and pages, because they are also paginated, and so you need something smarter, and Scrapy was perfect for us. And we were able to scrape 716 classical latent documents, which is about 14 million words, and we're planning to expand on this. And then for language modeling, so far we only have worked with statistical language model. We're also experimenting with recurrent neural networks, but so far this has been more reliable. This is CanLM. If somebody has done some natural language processing, you may be familiar with CanLM. What it does is basically frequency count and computing condition probability on substrings in our case. Otherwise, you usually use that for words. So, for example, you're trying to predict the probability of, I don't know, let's go to the X, and then to, for example, for example, the name of a person will be less likely than a place, because you have computed statistic on text, and that reflects on the of course, on the frequency of that happening. This library is actually written in C++, but it offers a nice command line tools to generate the language model. But the nice thing is that, of course, there is a Python binding. The Python binding cannot substitute the command line interface. However, it allows you to load the models once you have created them. So you have like the best of the two worlds, because you get C++ very fast, very efficient, and then you just load the model in Python and you're ready to use that. And then that's the Jigsaw oversegmentation. That's really NumPy plus OpenCV, old school computer vision, even though we're also planning to, with the new data, we're also planning to experiment with something that is learned rather than made through heuristics and lots of trial and error. And that's what we get. For example, what we're doing here is we're considering the upper and lower contour of this image. And when the upper contour and the lower contour seem to meet, for example, we have local minima here and local maxima here, then we perform a cut. And that applies to the whole. And that has been a pretty reliable heuristic in our text. Not perfect, but good enough. And then it comes to the transcription part. So here we have all of the possible combination. They're not really all of the combinations that are possible, because of course we know that in this kind of writing we go left to right. So we're proceeding just left to right, and then combining inside of in the context of a window, because we know that characters can be larger than some threshold. You can expect a character to be ended within a certain amount of pixels. So there is no point in connecting the very first node to the very last one, because you know that that's simply not possible. So this is what we get. That's all the combination, of course, right to left, left to right, and within a window. And then each of these images that are also the edges of this directed acyclical graph are given to the neural network that is able to tell which one is a character and which one is not. Notice that even if we have wrong segmentation, taken in isolation, this could actually be characters, because this, okay, great. This could be an I, this could be a D, the example that we were mentioning earlier. And so simple visual recognition just can do that task. And then what we do is we traverse this graph, generate the transcriptions, and then rank them. So here we go. Oops. I thought there was an animation here, sorry. And so, for example, possible transcription from this graph are dato, dito, dai, de, di, id, di, I, d. And since we are able to compute the probability according to the Latin language, to the Latin substrings, of course, we are able to rank them, because hopefully this will be more likely than this, which will be way more likely than these two other transcriptions that are pretty much obviously wrong if you know Latin. The QR brings you to the website of the project. That is the data set we have been using and the publications if you want to go in more detail. And this is the results we have been achieving. Actually, these have improved from this kind of graphs, because here it says 65% of correct transcriptions, and 80% plus has at most 2 errors, as in typos, for example, an F being mistaken for an S, and so on. And now we are getting to 75% accuracy, according to our latest tests, because we have been tuning and improving each single part of the pipeline that I've been showing you. And that's a very good result if you consider the fact that our neural network error probability is of about 94–95%. And that seems very, very good, but it's actually not when you're working character by character. Well, it is good, but it's not as good as you would expect, because every time you predict a character, you have a 6% probability that that character will be wrong. Now, since these are probabilities, they stack on top of the other. And so, for example, if you have 95% accuracy and you multiply it 5 times by itself, then you have an exponential, and the best accuracies you can get gets being an exponential, it gets very low very fast. So theoretical limit would be around, with the model we're working with right now, would be 82% or so, and so being at 75% is very satisfactory for us. But of course, there is still work to do. And here you can see how good it gets depending on which language model you choose. This is with the substrings of size 3, 4, 5 to 8. And this is how good we get at the first transcription of the ranking, and this is at the top 3. Now you see when we're using 6 grams, more than 60% of the transcriptions are actually in the top 3, and or they are in the top 3 with 1 error or with 2 errors at most. We're considering this error as edit distance. I don't know if you're familiar with that, but basically it would be they either have a typo, so one character is mistaken for another, or one character is missing or added. So this is what we have been working on, and I will be glad to answer a few questions. Thank you.
Hello, thank you for the great presentation, very interesting. I was wondering, when you mentioned you get several different possibilities of possible words, right? Suppose there are two words that are equally valid in the Latin language. How do you decide? Do you check the surrounding words on what would make sense? Or?
Yes.
Okay.
Okay, so far we haven't implemented it yet, but of course in that it won't, right now we're having a bag of word approach. That is, every word is being transcribed in isolation from the others. But of course, if you are able to get the context, then it can be way more obvious what's going to follow. Especially because in this kind of text, it's very formulaic. Being letters and formal letters, they have a very specific way of speaking. The problem with that is that it's very hard to get an accurate proper language model, because if we're working with substrings of words, then you can say that classical Latin is fine. But when you're working at a sentence context level, then you need to get a text that you will be as good as your language model, and you need a language model that looks like your data. So, and that's harder to get. That's one issue we're having. The other issue we're having is that, as I mentioned, there is lots of abbreviations in the text. About 50% of the words are abbreviated. And in some cases, it can be easy to solve these abbreviations, because sometimes they use a very specific symbol. For example, the 7 I showed you earlier is actually an abbreviation for the conjunction word at. And then there is such kind of abbreviations where you can just add another symbol to your classification, but then there is a whole different set of abbreviations that depend heavily on context. And what's harder is that they do not have a specific symbol that identifies them. So you will have the same symbol one time meaning one thing and one time meaning another. And they are not specific at all. And that's very hard to cover, and that causes our text to be a bit spotty, because sometimes you won't get a full transcription. For example, you will get a very frequent one is EPO with a dash on it, meaning episcopo. But our current system is able to say EPO, is not able to say episcopo. So we're working on that. We have statistics on how often they occur, but it's a very long tail, because it's the same symbol using completely different context. Whereas when we have a symbol that is clearly identifiable and usually means a set of things, then we are already extending our capabilities to recognize that.
Other questions? Okay, maybe we are all waiting for beers this time.
Yeah, I guess so. It sucks to be the last speaker, but thank you for being
thank
here.
Thank you too, and
for being this strong.